Hello, students. This is our practice problems video for Module 10. The questions involve regression and correlation. Well, we have 4 questions here. The first 3, we use Golub data. Number 1, I give you the gene names as listed in the second column of Golub.gene names. We want to use the expression values for these 2 genes, find the correlation coefficient, and then we want parametric 90% and bootstrap 90% confidence intervals for this correlation coefficient. Well, we are using library multitest and the Golub data. Then I can look for the correct rows. So you notice this 0202 oncogene is in row 2714, and the other 0303 oncogene is in row 2715. So this is letter A. Here is the correlation coefficient. We have 0.7966283. Next one, we want a parametric 90% confidence interval. Well, we know that core test will give us a confidence interval, but the default is 95%. So I have typed question mark core.test, and you see we have this option where we can specify 0.90 to get the correct confidence interval. So let's do that. Here you can see we have the 90% confidence interval, and so my answer is here. This is the parametric 90% confidence interval, 0.670 to 0.878. Now, for the bootstrap confidence interval, let's use 2000 here. And then in the bootstrap confidence interval, we need to keep the dependency structure. And so when we resample the pairs together. First, I have created this, really it's a matrix data where I have column for row 2, column for row 3. Then we have our for loop. Here is where I have resampled with replacement, and I've sampled the pairs together. Okay, so then we store in this vector boot.cor the correlation coefficient on this pseudo data set. Okay, so now I can ask for the quantiles. Here's my bootstrap confidence interval. This was the end of letter C. Now we can move on to number 2. Instead of clearing my saved objects, when I look at number 2, I realize I'm working with the exact same 2 genes in the Golub data, so I will keep those variables. In number 2, I want to perform regression. Here, the GRO3 variable is my Y, and the GRO2 variable is my X. We can ask for summary. What do we see? The question is there a statistically significant linear relationship between the 2 genes expression? And then we have to answer the question, what is the proportion of variation that can be explained by this linear regression model? Well, for the first part, is there a statistically significant relationship? There's really 2 places we can look. One is the p-value on the t-test for the slope. And you notice this is very small. We would reject the null hypothesis that the slope is 0 and conclude there is a statistically significant linear relationship here. But then we could also look here on this p-value for the F statistic. This is something we talked about in one of our lecture videos. So maybe I will make this as a comment. All right, here's the comment in R. On the PDF of the solutions that I include in Canvas, I will have this typed nicer. But yes, there is a statistically significant linear relationship. Hello, I am splicing in this part of the video because I realized after recording, I forgot to answer a question. So let's answer it now. We are on 2A. What proportion of the variation in growth 3 oncogene expression can be explained by regression on growth 2 oncogene expression? Okay, this is in the summary table. We look here at the multiple R squared. So let me make this as a comment. And here is my comment: the proportion of variation explained by the regression model. Well, it's here, this R squared, 0.6346. Now, I'm going to take you back to the original session in which you won't see this on the R, but we have discussed it. Okay, next question in B, we want to test the following hypothesis regarding the slope. Beta 1 at the alpha is 0.05 level. The null hypothesis is that beta 1 is a half. The alternative hypothesis is that beta 1 is less than a half. What is your conclusion? Well, how are we going to do this? This is not included in the summary. This p-value is testing beta 1 equals 0 versus beta 1 is not equal to 0. And that is a different t-test. What we need to observe here is that we know there's a relationship between a t-test and a confidence interval. And we know how to make confidence intervals for this regression model. So we can convert a two-sided 90% confidence interval to a one-sided t-test at the alpha is 0.05 level. You notice in B, this is a one-sided t-test. The reason is because for a two-sided confidence interval, at the 90%, we have 0.05 and 0.05 on each side. Okay, so let's figure out a 90% confidence interval. So for the slope, a 90% confidence interval would be 0.2817 to 0.43468. Now let's make our observation about a one-sided confidence interval and then our t-test. Therefore, a one-sided 95% confidence interval that gives an upper bound on beta 1 would be here, minus infinity to this number, 0.4346801. Okay, the next observation is that a half is not in this confidence interval. Here is my final conclusion. As 1/2 is not in this confidence interval, we can reject H0. The data suggests that the true slope is less than a half. So as a remark, you see the estimate of the slope is certainly less than a half, 0.35820. However, we used a hypothesis test to conclude that not only the estimate was less than a half, but the true slope, beta 1, is less than a half. That was kind of a challenging question, but a wonderful blend of ideas. Letter C, find an 80% prediction interval for this y value, GRO3, when GRO2 is not expressed. That means 0 expression. Well, we learned how to make prediction intervals using R in this module, so we can just call this. So here's our prediction interval. You'll notice this estimated value when GRO2 is 0. This is just the intercept. But the question asks for a prediction interval, and that is here. It goes from minus 1.268 to minus 0.476, approximately. Okay, letter D, check the regression model assumptions. Can we trust, well, basically what we have just done? So we have two plots We also have a Shapiro-Wilk test. Okay, this is a little bit concerning. This is the plot where we have the fitted y values versus the residuals. We should see the mean approximately 0 throughout. We should see no obvious pattern. We should see approximately equal variance. And this doesn't seem to look like this. This plot is concerning to me. From this plot alone, I would say perhaps we shouldn't trust the inferences made from this linear regression fit. Well, we can also check if the residuals are normally distributed. Here is our QQ plot. In the middle, it looks okay. On the edges, it's a little concerning. It's not the best looking QQ plot we've seen this semester. If we run a Shapiro test on the residuals, well, this is not statistically significant at the alpha's 0.05 level. So perhaps we can say the residuals seem normally distributed, but this first plot, this is not what we're looking for. So maybe we don't trust the statistical inferences, as I mentioned before. Now, we can move on to number 3. We are still working with the Golub data. Here, we want the ZYXIN gene expression values. So we can look in Golub.gnames in the second column. We see the row is 2124. Okay, now what is it that we want here? How many of the genes have correlation values less than minus 0.5? These would be genes that are highly negatively correlated to ZYXIN. Here we want to use the apply function. You notice I'm applying to the rows of the Golub data set. Recall that each row corresponds to a different gene. This function that gives us back the correlation coefficient between, well, a given row and this ZYXIN gene. Now, we want to know how many have correlation coefficient less than negative 0.5. And that would be here. The answer is 85 genes. Letter B. We want the gene names of the top 5 genes that are most negatively correlated with the ZYXIN gene. Okay, we can order this vector where the smallest values are at the beginning, and then we go to the Golub.gnames second column to pull off the gene names for the first 5. Okay, here they are. 1, 2, 3, 4, 5. Letter C. Using the correlation test, how many genes are negatively correlated with this ZYXIN gene? Use a false discovery rate of 0.05. Okay, this is a wonderful example where we are performing a statistical test many times. And so we definitely want to adjust for multiple hypotheses here. We are going to use the apply function again. We apply to the rows of the Golub data the function where we run this core.test and then ask the p-value. Okay, this is my unadjusted p-values. Now I can use the p-adjust function, and I'm using a Benjamini-Hochberg correction here. We can ask how many of these adjusted p-values, we know really they're q-values for Benjamini-Hochberg, but how many of these are less than 0.05? And the answer is 142. So this is my answer to letter C. Last question, we have multiple linear regression. We want to use the data stack loss that's built into R. Let me clear all my saved objects first. I am done with the Golub data. So I will attach this stack loss. Now, if we want to look at this data to get an idea about it, here we go. We have four variables. One is stack.loss. R tells us this stack loss is a dependent or Y variable here. And then the first three variables, these are our explanatory or X variables for our multiple linear regression. We have airflow, we have water temperature, and then we have acid concentration. Well, let us fit a linear regression model where stack loss is my response variable, and then the other three are my explanatory variables. We can ask summary here. What are my questions? What is the fitted regression equation? Well, here are all, the estimates come in the first column, so maybe I will type this. Here is this fitted equation. The numbers came from this estimate column. Minus 39.92 is my intercept. And then I have 1, 2, 3 coefficients, beta 1, beta 2, and beta 3 that go, well, in front of the corresponding variables. All right, next question. Do all three variables have a statistically significant effect on stack loss? And then what proportion of the variation in stack loss is explained by the regression model? Well, if we look over here at these p-values, this one is not statistically significant. So for letter B, my first comment is here that acid concentration does not have a statistically significant linear effect on stack loss. It's because of this high p-value, but the other two variables do. What is the proportion of variation explained by the regression model? That is here, this multiple R squared. I will just copy and paste this. That's a lot, 0.9136. Okay, part C, we want a 90% confidence interval and 90% prediction interval for stack loss when, well, the airflow is 60, the water temp is 20, and then acid concentration is 90. Okay, we use the same function, just one of them we declare interval equals confidence for confidence interval, and the other we declare interval equals prediction for the prediction interval. Let me run both of these. The first one is the confidence interval, and it's here. Goes from 13.5 to 16.97. The second one is the prediction interval. This one is much wider. Prediction interval goes from 9.33 to 21.14. Well, thank you so much. This is the end of this practice problems for Module 10.